Hey guys, it's Josh Myers, and I am going to be bringing you the second part of the molecular orbital theory video that I started the other night. Okay, so in the last video we discussed the idea of the orbital and how it is the thing that is underneath the energy level. What is underneath the energy level, and then we talked about their shapes and then how as you move across the periodic table, as you add more electrons as you move from hydrogen to helium to lithium, all the way to neon, all the way to argon, and beyond. And beyond, you add one electron each time. And then we talked about how when you add these electrons, how they pair together. How each orbital contains a maximum of 2 electrons. And how the electrons added in the different elements as you move through can be paired in these orbitals. So for example, when you move to boron and then to carbon, those 2 added electrons are paired in what is the px orbital. Move to nitrogen and oxygen, that is the py orbital. And then finally, fluorine and neon, those electrons are contained in the pz orbital. So now what we are going to talk about to complete this more complete this concept of the molecular orbital theory is exactly what happens leading up to the neon atom or the argon atom or some atom on this side of the periodic table, and exactly how these orbitals go about being filled. And this has to do with energy. Okay, so let's erase this first part. It doesn't really, we know this now, it doesn't really help us too much anymore. Okay, all right. So the filling of the energy levels has to do with the energy states of the different orbitals relative to each other. And what this means is, for example, the lowest energy orbital is the 1s orbital, and that is why it is filled first, because it is the lowest energy orbital, and thus the electrons are in the state closest to the nucleus, or the state in which they will be in this idea that we call energetic favorability. But first, so the filling of the orbitals is what we're going to talk about. The filling of the orbitals. This has to do with the stabilization of the element. The state of filling these orbitals that gives it the most stability. And so, Josh, you're going to ask, Josh, what is this? What are these energies relative to each other for the orbitals? What determines this sort of energy thing? And so one of the quickest determiners of any sort of energy state we call energy state of orbital is the energy level itself, though it is not the only determiner, because as we will see as we look at this idea further, there are some orbitals that are in lower energy levels that are of higher energy than orbitals in higher energy levels. And this seems kind of counterintuitive, but this is why we are discussing orbitals, because it is so important. Energy state of orbital. Okay. And so the easiest way to just remember these energy states as we move across the periodic table. So this hydrogen and helium will be the electrons will be in the 1s orbital. Lithium and beryllium, the electrons added will be in the 2s orbital. And then from boron to neon, these electrons will be part of the 2p sublevel, particularly the px, the py, and the pz orbitals. And now as we see move across 3s and then the 3p. And so this is exactly how we progress through the periodic table. So if we were to list out the orbitals in order of energy, in order of the amount of energy they possess when electrons are in them, we would say that s orbitals are of lower energy than p orbitals. We would state them as, hold on a second, so much erasing. This is really difficult task. Now I've resorted to erasing with the bottom of the eraser. Okay, so now, if you were to list these orbitals in order of energy, we would say 1s, 1s, 2s, 1s, 2s, 2p, because we know that the first energy level does not have a p sublevel, so 2p, and then 3s, and then 3p, 3p. And so this is exactly the sequence in which the electrons begin to fill these orbitals. In any way, even the electrons that are possessed by fluorine, the first electrons fill the first energy level. So there are 2 electrons that fill the first s orbital. And then they go to fill the 2s orbital, and then finally 5 electrons in the 2p sublevel. And this is exactly how elements go about filling their outer shells. And this is why we have talked about previously drawing atomic structures, but now we will talk a little bit more behind the theory of exactly according to orbitals, exactly what these atomic structures look like from a stance of how many electrons are in each orbital. So before we do this, let's just write a solid rule just so we can all remember, and it is called the Aufbau rule, the Aufbau rule. And what it says is that electrons fill lower energy orbitals before filling higher energy orbitals. Higher orbitals. And this is exactly what we've been saying the whole time, that they are simply in a more stable state when the electrons are filling the 1s energy level, the 1s orbital, and then the 2s orbital, then the 2p sublevel, 3s, 3p, and so on. And so now what we will come to do is it's very easy to discuss the idea of energy in orbitals if we draw these box diagrams that essentially will display each orbital and then the electrons in the orbital. So let's pick, for example, let's draw the sodium box diagram. And I know you do not know exactly what I'm talking about right now when I say box diagram, but it will become very clear momentarily. Okay, so sodium. And we know that sodium has a complete first and second energy level, and that it has 1 electron in the 3s orbital. Okay, so now the easiest way to draw these diagrams is to talk about the y-axis in terms of energy, so in terms of our rising of energy. So energy, and then, so let's look at the first orbital, the lowest energy orbital, and that is the 1s. So 1s. And this orbital is represented by a box. In the perfect world, everything would be boxes because they are easy to fill. It's like the mind, you put knowledge in it, or maybe, I don't know, maybe you just pull knowledge out of it. I don't know. You have to ask the philosophers about that. But so the 1s orbital box. And the way we show these electrons in this box, because we know there are 2 of them if we are talking about sodium, is that we draw one arrow up, which represents one electron, and then one arrow down, and that represents the second electron. And what this is really saying is that these two electrons in this orbital, the oppositely directed arrows represent an opposite spin. And I know this sounds like a very abstract concept, and I'm not really sure if I quite understand it yet either, but they represent opposite spin. And this essentially means, if I understand this from my perspective, is that the electrons, one is spinning clockwise relative to the nucleus, and then the other one is spinning counterclockwise relative to the nucleus. And so, what this creates, these atoms possessed in this same orbital, this opposite spin, creates a sense of stability. And this has a lot to do with quantum mechanics, but I will not necessarily talk about this because it is a very deep subject. We'll talk about, so the opposite spin creates stability, energetic stability, because that is exactly what we will be talking about this entire video, is the idea of energetic stability. Okay, so now the 2s orbital, because it has to be of higher energy, because it is more energy, possesses more energy than the 1s orbital. So 2s orbital, lithium and beryllium, the electrons that represent them, it also has 2 electrons and they have opposite spin. Okay, now let's move to 2p orbital. The 2p orbital, and it has, 2p sublevel. I will mix these words up very, very much throughout this video, I am guessing. And it has 3 orbitals. Okay, and we know if we go from boron, carbon, nitrogen, you would think maybe that you put, two arrows here and then one here. Well, this is actually not correct, and a man with the last name of Hud actually he was the one who discovered this, how these orbitals are filled. And these orbitals are filled where the orbital is at greater energetic stability when it is half filled than when it is not filled at all. So what he found out was that before any orbitals, any boxes can be completely filled, one electron going one way, one going the other way, they must be half filled for the sublevel. So what this means is that boron, the electron represented by boron, will be put here in the px orbital, but then the next electron representing carbon will be put in the py orbital, and then the next electron representing nitrogen will be put in the pz orbital. And see how in the last video I actually lied to you. I said that these two were paired just to make things easier, just to make it make sense at that point. But what we really understand is that these 3 electrons represent 3 different orbitals being half filled. Now finally moving to oxygen, now we completely fill the first one. Moving to fluorine, completely fill the second one. And then finally neon, having the complete outer energy level, the second energy level, completely filled, will fill the last one. And this represents a state of stabilization. Stabilization, we will just keep writing this word, stabilization. This is one reason why the noble gases are so unreactive. The biggest reason is because they are so stable. Their electrons are so happy where they are in their orbitals. But now finally we are talking about sodium. So sodium has now 1 electron in the 3s orbital. So now 3s. Let's draw our box. And it has 1 electron, which means that the 3s orbital is half filled. And so this is exactly how, using orbitals, we can represent elements in terms of the filling of the orbitals. And this filling is so important because it determines, again, the stabilization. And so as we saw in the last example, we have to half fill the orbitals before we can completely fill them. And this is because of the idea, again, that they are more stable when they are half filled. And so you have to half fill them before you can completely fill them. So now that we got that off our chest, Now let's talk about this example first, because there are a lot of implications of this idea of the stabilization. The stabilization. Let's actually erase up here because I like this little diagram. We can leave it for now. Okay, all right. Let's do that. Okay, so now that we've discovered this general idea, let's solve this first problem that we posed in the last video of why is the ionization energy of nitrogen greater than the ionization of oxygen, even though the general rule is that as you move to the right in the periodic table, the ionization energies should increase because of the relative attraction of the electrons to the nucleus as you move across a period. Well, if we draw out the diagrams for nitrogen, if we draw out the diagram for nitrogen, let's do that for a second. Let's erase sodium. Sodium now is the loner. He is not needed anymore. Okay, we are all needed as people though, and I think that our society does an okay job of telling us that on a regular basis. Okay, so as we know, nitrogen has a complete 1s orbital given the fact that it is in the second period. So it has a complete first energy level, and that is represented by this. Complete 2s orbital because it is still further down than lithium or beryllium. And then finally, boron, carbon, nitrogen. So it has 3 electrons in its 2p sublevel. And that means that each p orbital is half filled. Nitrogen, let's write nitrogen. And as we remember, this represents a state of relative energetic stability. And when something is relatively stable, when it is stable, it has half-filled orbitals, it takes more energy to take away one of its electrons. So if we're talking about nitrogen here, to take away this electron, for instance, it would take more energy than if for oxygen, if we were talking about the orbital diagram of oxygen, you would add 1 electron here because it is 1 to the right of nitrogen. So because this electron is so stable in this half-filled orbital, it would take more energy to remove it. It would take more energy to remove than this oxygen electron. And this is simply again because even if you remove this electron, this orbital is still half filled, which means it still has some fairly decent energetic stability. And I know that sounds like a very vague explanation, but that's really what it is. It's just more, this electron has greater it determines more an energetic stability than this electron does when it completely fills the orbital versus half filling the orbital. Okay, more energetic stability. So that is why the ionization energy of nitrogen is greater than the ionization energy of oxygen, because when you are removing the oxygen electron, you are removing it from here, and that takes less energy than removing it from there, which is the nitrogen one. Okay, so now that big mystery is off our chest. We know all about that stabilization, that idea of the stabilization now. But now let's talk a little bit more before we wrap up this video, because I am starting to get a habit of making them over 20 minutes, and I think this one will be too. Let's talk a little bit about the implications of this sort of idea of being energetically stable. Stability. And this represents the idea of which states of what we call ionization. That different elements prefer to be in. And when we say prefer, we don't mean feelings, we mean energetically prefer. What makes them most stable? And so as we've previously talked about, the alkali metals, they would prefer to lose an electron, and we've talked about because of the idea that they gain an electron configuration similar to the noble gases. And this is true. This is very true. But if we talk about gaining electrons for the nonmetals, if we talk about oxygen, its main what we call ionization state. Ionization state. Ion state. And this is equal to a charge of -2 or 2 negative. And this is because it in order for it to be stable as an ion prefers to gain 2 electrons to again have an electron configuration like the noble gas neon. And so it would prefer to have its outer orbitals, its py and px and pz orbitals filled with 2 more electrons spinning in opposite directions from the other ones in order to gain this complete second energy level. Okay, so now I will leave you with this idea, and we will talk a lot more about the energy, the filling of the energy levels, and practice this filling in the next video. Alright, see you guys.